Welcome to the Deep Dives, where we cut through the noise and distill the most critical insights from groundbreaking research. Today, we're tackling a topic that has, well, vexed developers and users alike, really at the absolute forefront of AI development. I'm talking about the persistent and often perplexing phenomenon of large language model hallucinations. Now, for those of you deeply immersed in machine learning, data science, and mathematics, you know this isn't just some minor glitch, it's really a fundamental challenge. It impacts the trustworthiness, the reliability of these incredibly powerful systems. So rather than just scratching the surface, we're going straight to the core of a truly foundational paper, Why Language Models Hallucinate. This work, published by researchers from OpenAI and Georgia Tech, offers a refreshingly clear statistical and, crucially, socio-technical explanation for this ubiquitous problem. What's so compelling, I think, is how it utterly demystifies these errors. The authors aren't framing hallucinations as some mystical inherent flaw in advanced AI. Instead, they propose they are a direct and predictable consequence of how these models are fundamentally trained, and, perhaps even more critically, how they are subsequently evaluated. Throughout this deep dive, we're going to illuminate the precise statistical causes that make these errors arise in the first place, and then pivot to the systemic issues in our evaluation frameworks that, well, inadvertently reward incorrect guesses over the much-needed admission of uncertainty.
That paradigm shift you mentioned is truly what makes this paper so significant, I think. For too long, hallucinations have been treated as this almost intractable sort of philosophical problem of black box behavior that we just struggle to understand. But this research, it reframes them entirely. It moves them into the realm of statistically understandable phenomena. It applies a rigorous computational learning theory lens, drawing very clear and, I'd say, actionable connections to establish concepts in fields like binary classification. For anyone working with these models, for you listening, this provides a profoundly tangible and actionable framework. It allows us to think about hallucinations not as an enigma, but as a problem amenable to statistical analysis and mitigation. It's a critical step towards building truly trustworthy AI systems because it makes the problem concrete, quantifiable, and most importantly, addressable. The paper meticulously analyzes the origins and persistence of hallucinations in two main stages. First, their genesis during the initial vast pre-training of the base models, and then their subsequent persistence and even exacerbation during the post-training refinement, often through techniques like reinforcement learning from human feedback. This dual-stage analysis offers insights that touch upon the fundamental objectives driving both model development and evaluation across the entire field.
All right, let's unpack this with some vivid, concrete examples from the paper itself. They really bring it home. They provide a simple yet incredibly telling prompt to a state-of-the-art open-source language model, DeepSeek v3. The prompt was, what is Adam Tauman Kalai's birthday? If you know, just respond with DDMM. Now, what's absolutely crucial here is that the prompt explicitly, unequivocally, asks the model to respond only if it knows the answer.
Yeah.
Yet when DeepSeek v3 was put to the test, it confidently gave three entirely incorrect dates across three separate attempts, 0307, 1506, and 0101.
Right, it just ignored the instruction.
Exactly. It didn't just get them wrong. It ignored the explicit instruction to signal uncertainty and simply bluffed, confidently providing false information. This immediately sets the stage for the core problem, and it gets even more elaborate, showing the depth of these plausible falsehoods. The paper presents Table 1, showcasing responses from other leading models, ChatGPT, specifically GPT-4o, DeepSeek again, and Llama to the query, what was the title of Adam Kalai's dissertation? Now, for context, the correct title was Probabilistic and Online Methods in Machine Learning, completed in 2001 at Carnegie Mellon University. But here's the kicker. None of the models generated the correct title or even the correct year or institution.
Not even close, really.
Not even close. Instead, they confidently fabricated plausible-sounding but entirely fictitious titles and affiliations. ChatGPT, for instance, claimed boosting online algorithms and other topics in machine learning from CMU in 2002. DeepSeek offered algebraic methods in interactive machine learning from Harvard in 2005. And Llama suggested efficient algorithms for learning and playing games from MIT in 2007. What we see here isn't just simple factual inaccuracy, it's the generation of confidently presented, plausible-sounding falsehoods.
Exactly, and that, as the paper argues, is precisely the core phenomenon we refer to as hallucination in LLMs. It's not just a miss, it's a confident yet utterly false creative fabrication. This immediately raises the central question that the paper seeks to answer. Why do these highly sophisticated models produce such overconfident yet utterly false plausible statements? The paper defines these hallucinations very formally, categorizing them as a specific subset of errors, which they term plausible falsehoods. These exist within a broader universe of plausible strings, X. So X is comprised of two distinct sets. V, the set of truly valid and correct strings, and E, the set of errors, which crucially includes these plausible falsehoods. This formalization is vital because it moves the discussion from anecdotal observations to a rigorous classification problem.
Right, putting a mathematical structure on it.
Precisely, and the central thesis of the paper is profound in its simplicity, yet incredibly insightful. Language models hallucinate because our current training, and critically our evaluation procedures, inadvertently but systematically reward guessing over acknowledging uncertainty.
So it's baked into the system.
It's a deeply socio-technical problem, baked right in. In essence, the authors argued that these hallucinations need not be mysterious. They originate simply as errors in binary classification. Think about it. If a model, during its generation process, cannot reliably distinguish between a correct factual statement, a valid string from V, and an incorrect yet plausible one, a plausible falsehood from E, then natural statistical pressures inherent in the optimization process will inevitably lead to the generation of these errors. It's a fundamental statistical misstep, not some mystical malfunction.
Okay, that makes sense. But what about persistence? Why don't we fix it in post-training?
Ah, yes. Furthermore, the paper posits a critical mechanism for the persistence of these hallucinations, even after models undergo additional refinement steps like fine-tuning or reinforcement learning. This persistence is attributed directly to the way our current evaluation benchmarks are constructed. These benchmarks overwhelmingly penalize uncertain responses, or outright abstentions like an explicit, response by assigning them 0 points.
0 points for being honest.
Exactly. This creates a powerful misaligned incentive. It effectively pushes models to guess, even when they are highly unsure, because guessing offers a non-zero chance at a correct answer, 1 point, whereas admitting uncertainty guarantees 0 points. The paper powerfully refers to this as an epidemic of penalizing uncertainty. It's a systemic issue that fundamentally misaligns the incentives in model development, driving models towards confident, albeit sometimes false, assertions rather than honest expressions of their knowledge boundaries.
That's a powerful and thought-provoking initial argument. So if these plausible falsehoods are indeed an inherent problem, let's dive into their very genesis, the pre-training stage. This is where the base model learns the vast, complex distribution of language from an enormous text corpus. The paper makes a bold and almost counterintuitive claim. Even if we assume this massive training data is completely error-free, a highly idealized scenario, I might add.
A very big if.
Right. Even then, the statistical objective minimized during pre-training inherently leads to the generation of errors. That feels like a crucial paradox. Where exactly does the statistical inevitability of error creep in? What's the underlying mechanism here?
This is where the paper draws a truly elegant and deeply insightful connection, one that should resonate profoundly with anyone familiar with classical learning theory, maybe you listening. The authors introduce what they call the "is it valid for" problem, effectively framing the generative task through a binary classification lens. Imagine a simple classifier tasked with answering a yes-no question. Is this a valid language model output?
Okay, like a gatekeeper.
Kind of. The core insight is that generating valid outputs, which is what an LLM does, is, in a profound sense, harder than this simple binary classification. Why? Because generation implicitly requires the model to answer, is this valid, for each potential candidate response it might produce, making the generative process inherently tied to this underlying discriminative challenge.
So generation includes classification, in a way.
Yeah. In a very real sense, yes. To formalize this I-5 problem, they construct a training set where responses are labeled as either valid plus or error, mirroring figure 1 in their paper. The crucial conceptual step is how they define the distribution D for this supervised learning problem. It's modeled as a 50-50 mixture. Half of the examples come from the valid pre-training data, which for this analysis is assumed to be pristine and thus labeled plus, and the other half are uniformly random errors, carefully constructed to represent plausible falsehoods and labeled B.
Okay, so mixing good examples with plausible bad ones.
Precisely. This ingenious conceptual setup allows them to establish a direct mathematical relationship, formalized in Corollary 1 and Theorem 1, essentially. The generative error rate is approximately twice the IFE misclassification rate, or more formally, generative error rate, US 2-point IV misclassification rate.
Wow, okay. So the error we see in generation is directly mathematically linked to how well it could hypothetically classify good versus bad outputs.
Exactly. This reduction is profound because it effectively takes a seemingly complex generative problem, an LLM creating novel text, and recasts it into a problem we've been grappling with for decades. Simple binary classification error. This isn't just an observation, it's a powerful reduction. It allows us to leverage all our existing knowledge about why classifiers make mistakes and apply it directly to understanding LLM hallucinations. It tells us that the how these errors arise is deeply rooted in fundamental statistical pressures common to all learning systems.
And how does calibration fit into this? You mentioned the cross-entropy objective.
Right. Let's connect this to calibration, a concept central to understanding the magnitude of these errors, especially in the context of the standard cross-entropy objective used during pre-training. The paper argues that the magnitude of miscalibration, denoted as GO, is typically quite small after pre-training. Why? Because models are usually optimized using the cross-entropy objective equation 3 in the paper. This inherently encourages the model's predicted probabilities to align with the true likelihood of the data. If goal were not small, meaning the model was poorly calibrated, it would imply that the model could easily reduce its loss by simply rescaling its output probabilities.
Which means it wasn't fully optimized.
Exactly. This, by definition, would mean the model is not at a local minimum of the loss function. Therefore, during the extensive multi-epoch optimization process of pre-training, models naturally gravitate towards a state where goal is minimized, leading to relatively well-calibrated probability distributions.
And is there empirical evidence for this?
Yes, this theoretical argument finds strong empirical support in Figure 2 of the paper, which presents GPT-4 calibration histograms. These plots visually demonstrate that pre-trained models are often remarkably well calibrated. Their stated confidence levels closely match their actual accuracy. In stark contrast, post-trained models, particularly after reinforcement learning from human feedback, RLHF, may deviate significantly from this calibration. This empirically supports the idea that good calibration, and consequently the inherent generation of errors, is a natural and expected consequence of optimizing with the cross-entropy objective.
So paradoxically, trying not to hallucinate might make a model poorly calibrated.
That's the almost paradoxical implication here, yes. Any hypothetically non-hallucinating Model 1 that somehow managed to avoid these errors entirely would necessarily be poorly calibrated. Its stated probabilities wouldn't align with its actual accuracy. But, as we've discussed, the cross-entropy objective relentlessly pushes models towards this calibrated state, highlighting the inherent tension between calibration and perfect accuracy.
Okay, and does this framework handle prompts, like when we give the model context?
It does. This analytical framework doesn't stop at simple, unprompted generations. It generalizes beautifully to scenarios involving prompts or contexts denoted as C. In this extended view, each example for the IIV problem becomes a pair, CR, representing a prompt and a plausible response. Theorem 1 generalizes corollary 1, applying the same fundamental relationship between generative errors and IIV misclassification to these prompted scenarios. It includes adjustments for factors like the ratio of maximum valid responses to minimum erroneous responses, max VC, minc EC, and of course the calibration term AS. This formalization precisely describes how density estimation, which is the core goal of pre-training, essentially learning the probability distribution of text given a context, directly contributes to error generation. It pushes our understanding far beyond a simplistic next-word prediction view of LLMs, connecting it firmly to the well-understood dynamics of misclassification in supervised learning.
That framework viewing generation as an is-it-valid classification problem truly is powerful. It really shifts the perspective. So it allows us to step back and ask, if these errors are indeed misclassifications, what are the classic culprits? What are the specific factors that decades of machine learning research have identified as driving such errors? And critically, how do they manifest in these massive language models during pre-training? The paper insightfully draws upon this extensive body of work to enumerate several key contributors.
Exactly. We can leverage that extensive body of work to pinpoint the factors. One of the primary factors discussed is what they term arbitrary fact hallucinations. This arises fundamentally from epistemic uncertainty, meaning there's no succinct generalizable pattern or necessary knowledge that can be reliably extracted or generalized from the training data. Here, the paper brings in the Vapnik-Chervonenkis, or VC dimension framework. For those who might need a quick refresher, the VC dimension fundamentally measures the capacity or complexity of a function class, essentially, how many distinct patterns a model can learn or shatter.
Right, the model's learning power.
Exactly. When it comes to arbitrary facts, like a specific individual's birthday, there's no underlying generalizable pattern to infer. Each fact is essentially an independent, high-entropy data point. The paper implies that the model's VC dimension, even if astronomically high, faces a fundamental limitation here. It can memorize, but it cannot truly generalize on arbitrary independent facts. This inherent difficulty in learning non-patterned information is precisely why these models are prone to hallucinating on such data. If a fact, like a particular person's birthday, appears only once, or very rarely within the massive pre-training corpus, it becomes incredibly difficult for the model to learn or reliably recall that specific piece of information. The model effectively has no strong signal to distinguish it from a plausible falsehood.
So how do they quantify that? The rarity of facts.
Good question. To quantify this arbitrary fact problem, the paper brilliantly resurrects a classic from the annals of statistical linguistics, Alan Turing's missing mass estimator, popularized by Good in 1953. For those familiar with language modeling history, you'll recognize the missing mass concept from early statistical linguistics, essentially estimating the probability of unseen events. Here, the authors apply it through the concept of the singleton rate, that's definition 2 in the paper. The singleton rate is defined as the fraction of prompts that appear exactly once in the training data without the model having the option to abstain. This is crucial because it gives us a concrete, mathematically grounded way to estimate how much novel, unrepresented information exists in the vast training data. This rate acts as a proxy, giving us an estimate of how much unique information remains unseen or underrepresented.
Okay, so the singleton rate measures the uniqueness or rarity of prompts.
In a sense, yes, and Theorem 2 then provides a lower bound for hallucinations in this arbitrary facts model. It states that the error rate error will be greater than or equal to error2 minc EC 35 plus 6 ln and s square RTN. This is a crucial finding. It means that if, for example, 20% of birthday facts appear only once in the training data, so error r equals 0.2, the model is expected to hallucinate on at least 20% of those facts minus some smaller terms. This analysis significantly strengthens prior work by Kalai and Vempala in 2024 by formally including the impact of prompts and the option of, IDK responses, making it more robust and directly applicable to real-world LLM scenarios.
Makes sense. What other factors contribute besides these arbitrary facts?
Another significant contributor to misclassification-like errors are poor models. These misclassifications occur when the underlying model, for whatever reason, cannot adequately represent the concept it's trying to learn, even if the data were abundant. This could be due to the inherent limitations of the model family itself. Think, for instance, trying to use linear separators to approximate a complex, nonlinear circular region. Or the model family might be expressive enough in theory, but the specific instantiated model simply isn't a good fit for the nuanced requirements of the task at hand. Agnostic learning, a concept explored by Kearns et al. Back in 1994, addresses the former by defining opt-G, the minimal error rate achievable by any classifier within a given hypothesis class G.
Can you give an example of a poor model in this context?
Sure. The paper vividly illustrates this with Theorem 3, pure multiple choice, and Corollary 2. Consider a classic trigram language model, which was dominant in the 80s and 90s. Such a model predicts words based only on the prior two words, a severely limited context window. The paper presents a compelling example. Imagine two prompts. She lost it and was completely out of her mind, and he lost it and was completely out of his mind. A trigram model, due to its inherent limitation of only looking at two preceding words, simply cannot reliably distinguish between her mind and his mind in these contexts, because the critical distinguishing pronoun, she or he, falls outside its context window.
Ah, I see. The model architecture itself is the limitation.
Precisely. Consequently, Corollary 2 formally proves that any trigram model, under a uniform distribution over these two contexts, must have a generation error rate of at least 12. Its inherent architectural limitation leads directly to an unavoidable rate of errors.
And we see this with modern models, too.
We do. We see a modern manifestation of this in the letter counting example from the introduction. DeepSeek v3 often yields incorrect numbers when asked how many B's are in DeepSeek. In stark contrast, DeepSeek R1, a reasoning model, reliably counts letters, sometimes even generated, I think the paper said, a 377-step chain of thought to do so. This isn't necessarily about the inherent data or general factual knowledge. It highlights that DeepSeek R1 is a better model fit for the reasoning task, capable of representing the concept of counting accurately through its specialized architecture or training. Whereas DeepSeek v3, as a general-purpose language model, is a poorer model for that specific type of query. The representational challenge here is particularly acute because modern LLMs tokenize text, often breaking words into subword units, which can significantly complicate character-level operations like precise letter counting. This illustrates how the choice of model architecture and its specific training objectives directly influence its susceptibility to certain types of hallucinations.
Okay, so we have arbitrary facts and poor model fit. Are there other major factors?
Yes. Beyond these core statistically grounded factors, the paper outlines several additional factors that contribute to base model errors. Firstly, computational hardness. AI systems, like any classical computer, cannot violate the fundamental laws of computational complexity theory. The paper demonstrates how Theorem 1, linking generative errors to I5 misclassification, applies even to intractable queries, such as decryption tasks. Observation 2 illustrates that for such queries, if a language model cannot efficiently break the encryption security, a task known to be computationally hard, it can only guess with a high error rate. In such a scenario, an "I don't know" would be a perfectly valid, indeed optimal answer. This shows how computational intractability in the underlying supervised learning problem directly parallels a significant factor for hallucinations in generative models. It's a reminder that LLMs, for all their power, are still bound by the limits of computation.
That's a fascinating link. What else?
Secondly, distribution shift. Errors frequently stem from out-of-distribution, prompts that differ substantially from the model's training data. Let's consider an example. Imagine a large language model primarily trained on highly formal academic texts, say, legal documents, scientific journals, and classic literature. Its entire world is structured, fact-checked, and precise. Now, suddenly, you prompt it to generate a whimsical, colloquial dialogue between two teenagers discussing pop culture. That prompt is wildly out of distribution compared to its training corpus.
Right, it's completely unfamiliar territory.
Exactly. The model's internal is-it-valid classifier, which learned the patterns and plausibility of formal language, simply lacks the statistical experience to accurately judge the plausibility of a conversational, slang-filled response. It's not that the model is poor in its general design, but it's encountering a domain where its learned distribution simply doesn't apply, leading it to generate plausible but incorrect or even nonsensical outputs because it's operating in unfamiliar statistical territory. While not a direct primary cause within the I4V framework itself, it significantly contributes to the statistical pressures leading to errors.
And the classic GI-GO problem.
And finally, yes, GI-GO, or garbage in, garbage out. This is perhaps the most straightforward and intuitively understandable factor. Large training corpora, by their very nature and immense scale, inevitably contain factual errors, biases, and half-truths. Base models designed to learn the statistical distribution of this vast text will simply replicate these errors. The statistical similarity between GI-GO and traditional classification problems where noisy labels lead to misclassifications and its impact on pre-training is self-evident. This factor is crucial because while the paper's initial analysis assumes error-free data to establish theoretical lower bounds on errors, real-world noisy data would naturally lead to even higher error rates in practice. GI-GO provides a natural bridge to understanding why hallucinations persist even after post-training, as the model has already ingested and internalized these errors.
So we've established how pre-training, even with clean data, inherently leads to the generation of these statistical errors. Lots of factors there. But then we layer on the post-training stage, which is explicitly designed to refine the base model, often with human feedback and with the express goal of reducing hallucinations. Yet the paper powerfully argues that not only do they persist, but they can even get worse. That feels like a crucial paradox. What's the mechanism, the perhaps unintentional training effect that keeps this guessing game alive even after we try to refine these models? What is the socio-technical explanation for this seeming paradox?
The paper introduces a highly relatable analogy here, one that resonates deeply with our human experience of learning and assessment. Consider students facing a challenging exam. When uncertain, students frequently guess on multiple-choice questions or even bluff on written exams, providing plausible-sounding answers in which they actually have very little confidence. Why do they do this?
To maximize their score, right?
Exactly. Because under a binary 0-1 scoring scheme where a correct answer yields 1 point and a blank or an "I don't know" IDK response yields 0 points, guessing when unsure actually maximizes the expected score. A bluff, often overconfident and specific, like confidently stating September 30 instead of hedging with sometime in autumn for a date question, simply offers a non-zero chance at that 1 point, whereas an honest admission of uncertainty guarantees a 0. It's a rational strategy for a test taker under those specific scoring rules.
And LLMs are acting like these test takers.
The paper insightfully argues that language models in many contexts are essentially forced into being these test takers. A vast majority of the language model benchmarks that currently define success and drive progress in the field mirror these standardized human exams, employing simplistic binary metrics like accuracy, pass rate, or exact match. Consequently, when we optimize models to perform well on these benchmarks, we are inadvertently fostering the very behavior we want to mitigate hallucinations.
So we're training them to guess.
Effectively, yes. Imagine two hypothetical models. Model A, which is perfectly aligned and correctly signals uncertainty by saying, I don't know, when it genuinely is unsure. And Model B, which is similar to Model A but never indicates uncertainty, always guessing when unsure. Under the prevailing 0-1 scoring metrics, Model B will always outperform Model A, because Model B gets some guesses right, earning points, while Model A gets 0 for its honest abstentions. This creates a powerful systemic epidemic of penalizing uncertainty and abstention. It's a deep flaw in our evaluation systems that fundamentally misaligns the incentives in model development.
Wow. So the benchmarks themselves are part of the problem.
Yeah.
Does the paper show evidence of this in current benchmarks?
It does, very clearly. This leads to a strong and meticulously documented critique of existing evaluation methodologies. Observation 1 formally proves this point. Under any distribution of binary graders, the optimal response for a test taker is not to abstain. Abstentions are strictly suboptimal in terms of expected score.
Mathematically proven suboptimal.
Exactly. This is a fundamental mathematical flaw in how we evaluate. The paper then provides a crucial meta-evaluation in Table 2, page 14, for those following along, analyzing a wide array of popular and influential benchmarks across the field. Benchmarks like GPQA, MMLU Pro, iFeval, OmniMath, BBH, Math, L5 Split, Musser-R, SWE-Bench, and HLE overwhelmingly employ binary grading. They offer no credit for I don't know or any other form of abstention.
Not at all.
Overwhelmingly no. Even WildBench, which uses an LM-graded rubric, implicitly suggests that an IDK response might score lower than a fair response that contains factual errors, further reinforcing the incentive to guess. This comprehensive analysis points to a systemic issue. Simply introducing more hallucination-specific evaluations isn't enough to fix this. The numerous primary evaluations that currently dominate leaderboards and drive model development must be adjusted to break this insidious cycle of rewarding overconfidence.
That's a powerful and quite sobering observation, that our very evaluation systems are actively reinforcing the behavior we're trying to mitigate. It's almost like trying to get a student to admit they don't know, but then punishing them for doing so. If it's such a deeply entrenched systemic problem, what do the authors propose as a practical and effective way to mitigate this issue? How can we realign these incentives to foster more honest and trustworthy AI?
The authors propose a socio-technical mitigation that is surprisingly straightforward in its concept, yet potentially profound in its impact: explicit confidence targets. Instead of the Herculean task of introducing even more bespoke, potentially niche hallucination-specific evaluations, the paper suggests a modification to the scoring of existing mainstream benchmarks. The core idea is to embed an explicit confidence target directly into the instructions of the evaluation task itself.
Okay, how would that work in practice?
Well, for instance, a question could be appended with a clear, concise statement like, answer only if you are T-confident. Since mistakes are penalized, T 1 points, while correct answers receive 1 point, and an answer of I don't know receives 0 points. A simple calculation demonstrates that the expected score of offering an answer only beats an IDK response, which scores 0, if the model's internal confidence in that answer is greater than 9.
So you make the penalty explicit, linked to a confidence threshold T.
Precisely. This directly and transparently calibrates the model's behavior with the scoring mechanism. The paper highlights natural values for T, such as 0.5, where mistakes are penalized 1 point, balancing correct and incorrect, 0.75, where a mistake incurs a penalty of 3 points, typo and outline script was 2, or 0.9, where the penalty for error is 9 points, heavily disincentivizing guessing. A T of 0, for example, would effectively revert to the current binary grading, implicitly telling the model, make your best guess, even if unsure, because there's no penalty for wrong answers beyond just not getting the right one.
And what's novel about just stating the threshold? Haven't people thought about penalties before?
What's truly crucial and novel here, distinguishing it from prior work, is making this confidence threshold explicit and transparent in the instructions given to the model. This transparency is vital for several reasons. It supports objective grading, removing ambiguity for both the model and its developers, and it helps achieve consensus among model creators on what constitutes acceptable risk and what an optimal model behavior should look like. While the ideal penalty, perfectly reflecting real-world harms, is often impractical due to its application-specific and subjective nature. By explicitly stating these thresholds, we provide a clear, actionable target for models to optimize against.
So it's about setting clear expectations for the model's behavior.
Exactly. This approach aims for what they call behavioral calibration, where the model intelligently formulates the most useful response in which it is at least confident, rather than merely outputting a probabilistic confidence score. This behavioral calibration can then be rigorously audited by comparing accuracy and error rates across different confidence thresholds in a post-hoc analysis.
And the key is putting this into existing benchmarks.
Yes, the key, therefore, is integration, not isolation. The proposal is to incorporate these explicit confidence targets into existing mainstream evaluations, like the highly influential SWE bench, which currently grades software patches with binary accuracy, rather than merely creating new, isolated hallucination evaluations. The latter would likely struggle to gain traction and widespread adoption against the dominant leaderboards focused on traditional accuracy. By strategically realigning the incentives within established benchmarks, we can encourage and reward appropriate expressions of uncertainty, fundamentally shifting the landscape towards more trustworthy, pragmatically competent, and ultimately more useful AI systems.
This paper provides a truly robust and thought-provoking framework for understanding hallucinations, offering both statistical routes and practical mitigation strategies. However, a hallmark of rigorous research is also a humble discussion of its own limitations and specific aspects that were deliberately simplified for the sake of clarity and focus. What are some of these important considerations the authors themselves highlight, and what do they imply for future work?
You're right, the self-reflection in the paper is excellent, providing important context for its scope. Firstly, they discuss plausibility and nonsense. Their analysis primarily focuses on plausible falsehoods, hallucinations that sound reasonable and coherent but are factually incorrect. It largely sidesteps purely nonsensical generations, which, thankfully, state-of-the-art models produce quite rarely. The authors acknowledge that while their current framework could theoretically be extended to include these nonsensical strings by simply expanding the definition of errors, the distinct nature of plausible but false is where the most pressing societal and trustworthiness concerns currently lie, and thus was their primary focus.
Okay, so focus on the tricky, believable errors. What else?
Secondly, they acknowledge a simplification regarding open-ended generations. For the sake of clarity and analytical tractability, most of their examples and formalisms are oriented towards single, factual questions with relatively constrained answer spaces. But hallucinations frequently arise in much more open-ended prompts, like write a biography about, or explain a complex concept. For these cases, the framework could define an error as any response containing one or more falsehoods.
Just a binary error or no error, even for long text.
Right. However, they also concede that it would be natural to consider degrees of hallucination in such nuanced scenarios, depending on the number, severity, and prominence of errors within a longer generation. This concept of graded error is not currently captured by their binary II framework and represents a valuable avenue for future research.
Makes sense. What about things like ORAG, using external knowledge? Does that solve it?
Ugh. A crucial and often overlooked point they make is that search and reasoning are not panaceas. While techniques like retrieval-augmented generation, or RAG, where models access external databases and advanced reasoning methods can demonstrably reduce certain types of hallucinations by providing more grounding. The paper points out that observation 1, the finding that binary grading fundamentally rewards guessing, still holds true for any language model, even those augmented with sophisticated external tools.
So even with ORAG, if the search fails or is ambiguous.
Exactly. If an external search fails to yield a confident answer or the reasoning process still leaves the model uncertain, the current binary evaluation system still rewards guessing over abstaining. Furthermore, our RAG and external search may not even address intrinsic hallucinations, such as miscalculations, logical errors in multi-step reasoning, or confabulations that arise purely from the model's internal statistical patterns rather than a lack of external information. So while these techniques are valuable tools in the fight against hallucinations, they don't solve the fundamental incentive problem inherent in our evaluation methodologies.
Good point. Any other major limitations discussed?
They also bring up the challenge of latent context. The paper's current error definition doesn't account for hidden context, external to the explicit prompt and response. This can lead to ambiguities where what appears to be an error might not be, given an unstated user intention. For example, if a user asks about phones, intending to refer specifically to landlines in a historical context, but the model discusses cell phones as the default, the error isn't immediately obvious from the prompt response pair alone without knowing the user's latent context.
The ambiguity of language itself.
Right. This relates to what we call aleatoric uncertainty, which is inherent noise or ambiguity in the observation itself rather than the model's epistemic lack of knowledge. Extending the model to robustly include such external contextual factors for judging errors would be an interesting and complex future direction.
And finally, the way models express uncertainty.
Finally, yes, they delved into what they call a false trichotomy beyond IDK. The paper's categories of correct, incorrect, and I don't know are, for all their utility, still an idealization. While the ultimate statistical ideal would be to score evaluations precisely for specific downstream applications with highly nuanced reward functions, this is often impractical and prohibitively complex to implement across diverse use cases. Explicit confidence targets offer a practical objective modification to our current crude scoring. Moreover, they acknowledge that there are far more nuanced ways for models to signal uncertainty than a simple ADK, such as hedging language, it is possible that some sources suggest, omitting highly uncertain details or even asking clarifying questions back to the user. While the paper focuses on the statistical factors governing the top-level decision of what is said, it acknowledges that a richer pragmatic competence in language models will be essential for truly nuanced and trustworthy communication of uncertainty in the future.
So what does this all mean for us? This deep dive into why language models hallucinate has meticulously peeled back the layers, revealing that these pervasive errors are not an inherent mystery of intelligence, but rather a predictable outcome of two core interconnected issues. First, the statistical pressures and objectives inherent during pre-training naturally lead to misclassifications within the model's internal is-it-valid assessment. And second, and critically, the deeply misaligned incentives embedded in our current evaluation benchmarks actively reinforce and even exacerbate the problem by penalizing honesty and rewarding confident bluffing.
It really boils down to that combination: statistical origins and evaluation reinforcement.
Exactly. The key takeaway for you, our expert listener, is that the path to more trustworthy AI lies not just in developing ever more complex models or inventing new, isolated hallucination evaluations. Instead, it points to a socio-technical mitigation, a fundamental rethinking of how we score what models say, and a conscious, systematic effort to reward honest expressions of uncertainty rather than penalizing them. This is a call to action for the entire field, urging us to redesign the very education system we've built for our AI.
If we connect this to the bigger picture, this research raises an important question for all of us shaping the future of AI. What kind of AI systems do we truly want to build? Do we want confident bluffers that prioritize appearing knowledgeable, even if it means generating falsehoods and undermining trust? Or do we want systems that are reliable, precise, and most importantly, transparent about the boundaries of their own knowledge? Modifying mainstream evaluations to incorporate explicit confidence targets could truly steer the field toward more nuanced, pragmatically competent, and ultimately more trustworthy AI systems. Imagine a world where our AI assistants don't just know the answers, but genuinely know when they don't know, and communicate that uncertainty effectively and appropriately, fostering a new level of partnership with human users.
A powerful thought to ponder as we continue to push the boundaries of AI, and a crucial reminder that our evaluation methods shape the very intelligence we create. We hope this deep dive has given you a richer, more statistically grounded and systemically aware understanding of the roots of LLM hallucinations. Thank you for joining us. Dive deeper into the research, question the assumptions embedded in our methodologies, and keep exploring.